Hey, what's up, everybody, and welcome back to the Sanctuary. I'm your host, Professor C, and I'll be taking us through another A&P study session. Today, specifically, we'll be talking about chemical bonds. Alright, today I'm going to go through some more details about chemical bonding. Now, if you've been watching the series, we've gotten to the point where we can draw some atoms using Bohr models, and we can make some predictions about, who's going to lose electrons, who's going to gain electrons, and how things will bond. But let's look at it a little bit more in depth here. And a good place to start, I guess, is just with the definition. And everyone knows what a bond is. We've mentioned it in several different ways in other lectures, but it's an attraction, right? And you can think of this as having a bond with another person. You say you have a bond with a person, you have some sort of special attraction that joins you two together in some sort of way. It's the same thing here with chemical bonds, but of course the relationship is going to be between atoms and how they interact with each other to form larger structures we call molecules. So we're moving our way, again, up into this next level of organization. We've dealt with the atomic level. Now we need to move on forward to the molecular level, understanding bonding. So even though there are more than these are typically the three, what we call major classes, and a lot of the other subgroups are just subgroups of these classes. So let's look at the big three and make as many points as we need to for a biology class. Ionic. There's no R there. I have had students call that ironic bond in the past. Ionic, something to do with an ion. Okay. Covalent. All right, fine. And we can kind of cheat a little bit already. If you've got literally 30 seconds to study for your test, this might be the answer. We're going to talk about, we'll show the details in a moment. This is a transfer of electrons, and this is a sharing. And that is the language that's used on many tests. In fact, all the ones that I've seen involving these bonding patterns use the word transfer and sharing. What are they sharing and transferring? Just to be clear, electrons. And when we talk about chemical bonds, that's what's happening, is atoms are trying to achieve stability, making their valence shell full of electrons. Okay, there is this kind of left behind guy that gets talked about at the end, a hydrogen bond, and we'll be mentioning them sometimes. You just hear this called an H bond. So there's the big three: ionic, covalent, and H bonding. All right, so we're going to start off with an ionic bond and take a look at some things we know from previous lectures. So let's go ahead and just say, hey, I know lithium. I've seen lithium before. 3 protons, 3 neutrons, 3 electrons. I can see the protons and neutrons locked up in the nucleus as they should be. And I see the 3 electrons distributed in the shells, as we learned about. 2 in the first shell, here and here. And then 1 out in that, what we call the valence shell, its outer shell, and only 1. So we know if it's got less than 4 in that valence shell, we can say this thing is electropositive. And we know that to achieve stability, it's likely to lose that electron rather than gain 7. It makes more sense that it would just lose 1 to achieve stability. Notice also that the number of protons and the number of electrons is the same. And that's the way it should be. If we're talking about an atom of lithium, they should be balanced like that. For every positive, we have a negative to balance it. So it's got a small electronegative charge or electropositive charge, but not an overall charge. Not yet anyway, right? So fluorine, one we have not seen before, an atom we haven't seen, 9p, 9n, 9e. Again, we see that everything is balanced here as it should be. For every positive charge we have a negative charge, so this would be known as a fluorine atom. And just to recap, we've got inside the nucleus here 9 protons and 9 neutrons. And so we know the electrons go in the shells beyond, 2 in the first. And if we take away 2 from 9, that would leave 7 for the outer shell. That's what we have there. The number of valence electrons is 7. I can put that over here just to make sure we're doing everything correctly. So 7 valence electrons. Again, if it's more than 4, we're going to say that's electronegative, according to our rules we established on previous lectures, and it is likely to gain electrons to achieve stability, which makes sense because we see the red arrow here pretty much telling us what's about to happen, right? So fluorine wants to gain 1 to achieve stability, and lithium wants to give up 1 to achieve stability. So how convenient. So I think what we can do now is, after we've set it up here, let's watch what happens after the transfer, right? If this guy goes away and joins this, we don't have the same kind of formula, if you want to call it that. Now we have 3p, that hasn't changed, the number of protons didn't change. 3n, that didn't change, the number of neutrons didn't change. But we only have 2 electrons now, right? Because we gave 1 up. There is an imbalance now between the 3 protons that are positive and the 2 electrons. Can't balance that out, right? So what we do is we now write lithium as Li as we did before, but we put a plus on it, a big giant plus charge, not just a little electronegative or positive charge with a squiggly symbol. Now we put a big plus, telling me this is no longer a lithium atom, but this is now called, if I can spell a 3-letter word correctly, this is called a lithium ion, an ion. Remember, because it's not balanced anymore electronically. It's got more positives than it does negative. This is after it's given its electron up, right? Okay, same thing with fluorine. We know what it looked like before, 999. It's picking up a new one that it didn't have. So after the transfer, it's going to be 9p, didn't change proton number, 9n, didn't change neutron number, but now we have 10 electrons, right? Which is more than we had. 1 more. It's full. Yep, everyone's full and happy, but we have an imbalance again. We have 9 positive charges and 10 negative charges. Okay, if we write fluorine as F, just like it is on the periodic table, we wouldn't just call this a fluorine atom anymore, right? It's got a negative charge to it. So actually we changed the entire thing. We call that a fluor, and I'll just put the ending here. It's called a fluoride ion now. Instead of calling it a fluorine atom, it's now called a fluoride ion, all right? That's just the terminology that's used in chemistry. Now, the important part for us is when this positively charged atom here, okay, cation is what that's called. A positively charged ion is a cation. It looks like cation, right? It looks like the word cation, but it's actually cation. And the negatively charged one is called an anion. And when these cation and anion see each other, they have an attraction electronically. Opposites attract, right? So that becomes LIF. And we smush the words together. The chemical symbols are smashed together into one symbol, lithium fluoride. And that was how an ionic bond is formed. Again, it's formed because of the complete transfer of electrons. And then after the transfer, the attraction of the charges makes an ionic bond. Okay, let's look at another example of an ionic bond, the classic example, table salt. There's the chemical symbol for table salt, something everyone's familiar with. It looks like NaCl, right? But we know this is sodium, and that is chlorine, and we can go peek up here at what we're about to do. But remember, we're going to call that sodium chloride, and it's telling us that sodium is going to turn out to be a cation, a positively charged ion, and chloride will turn out to be the negative component. And then after the transfer of electrons, these will have an attraction to each other. So let's draw this out real quick. I'd put 11 protons and 12 neutrons in the nucleus. I need to make a shell here for the electrons, but I know only 2 can fit here. That leaves me 9. And I know 9 can't fit here, only 8 can. But I'm going to fill it up, but it's going to leave me with 1 left over. So I'm going to have to make another shell way out here. And it's only going to have a single valence electron. So just to remind ourselves, it's got less than 4. So it's electropositive, and it's likely to lose electrons, but it hasn't yet. Okay, chlorine is a little bit bigger, and I'm going to try to squeeze it on here, so bear with me. So 17 proton and 18 neutrons go in the nucleus. I know I have 2 electrons here in this first shell, but I need to get 15 more. So I can put 8 here. That gives me 10 total, but I'm still lacking 7. So if I can fit a third shell here and put 7, 4, 5, 6, 7. There would be 2 correct Bohr models. A little squiggly, but we get the idea. And this should look, now that we see it, it should look quite familiar to the one we just did on the previous page with lithium and fluorine. It's going to have the exact same idea. The chlorine, again, it's got 7 valence electrons now, making it electronegative and making it likely to gain electrons to become full. And that's exactly what's going to happen. This one is going to jump over and join here. Then the sodium will be full and the chlorine will be full, but they're not going to be atoms anymore, right? We started with a sodium atom and a chlorine atom, but there's an exchange happening now, right? There's a transfer of electrons, a complete transfer from one to another. After the trade, let's say, there's still 11 protons and 12 neutrons. But now, since it lost 1, there's only 10 electrons. So there's a deficiency. So now we can call sodium ion. We can call this an ion now because there are more positive charges than there are negative charges. So this can be written in a plus, a sodium ion, instead of an atom. We can do the same thing with chlorine, and after it finishes this complete transfer, it will still have 17 protons, 18 neutrons, but now it will have 18 electrons, right? Because it picked up 1 from the sodium. And again, this is an imbalance now, but in the favor of the negative. So chlorine becomes chloride, a chloride ion. And then, of course, once we have the positive sodium and the negative chloride, these will stick together and form what we call table salt. All right, and of course you know that salts make crystals, but the point here is there are more than one type of just salt. Table salt is one example. And the way these things will interact is exactly the way we described it. Many of these atoms will come together and they will all be doing an ionic transfer simultaneously, and they'll form these large crystals of salts. So there are many types of salts, and they form these types of crystals in a very, very regular pattern. Okay, covalent bonding. So if, let me change my color, if we said that ionic bonds are a transfer of electrons, like a complete transfer, we're going to make the point here that covalent bonds are formed by sharing electrons. And that is like it sounds like. They're going to temporarily hold the electrons to be full, and then they'll give them back to their partner so they can be full for a little bit of the time. So it's kind of like, as this next phrase will tell us, it's kind of like 2 kids throwing a ball or balls or pairs of balls, even juggling with each other back and forth across a distance. Very similar to what's going on here. I'm full for a little bit if I have the ball, but when I throw the ball to you, you're full temporarily, and then you throw it back and I'm full, and then we throw it back to you and you're full. This is a sharing. This is a covalent bond. So this allows us to make, as you see in that top picture there, long carbon chains and rings, and we can form all sorts of polymers, right? Long pieces of small things using covalent bonding. And it's usually drawn as a solid line in a lot of pictures. And we see that down here, this HOH. Looks like there's a line there. This one's got 2 lines, though, and this one's got 3 lines. Remember, in an ionic bond, we just smash the letters together. Here we see these lines here, kind of indicating that there is some sharing going on. And I see that here. I can look here and here, and I see those green electrons belong to the oxygen, and these yellow electrons belong to the hydrogen. The hydrogen needs 1 to be full, so it borrows that from oxygen momentarily. But then the oxygen needs, 2 to be full because it's only got 6 valence electrons. So it grabs another hydrogen and takes both their electrons temporarily. So sometimes this pair here is around the oxygen. Sometimes it's around the hydrogen. Same thing here. Sometimes this 2 pair is around the oxygen. Sometimes it's around the carbon. And they're passing it back and forth. Sometimes this pair is around the oxygen. Sometimes around the carbon. They pass it back and forth. Nitrogen with itself will make 3 covalent bonds. It will share 3 pairs of electrons. Definitely like kids juggling now, juggling 6 electrons back and forth between each other. So each one's temporarily full, and they get this fullness, this stability, by passing them back and forth and back and forth and back and forth. The sharing, however, does not have to be equal. The way I just described it was 2 kids playing fairly and sharing equally, where one kid has the electron, then throws it back. Now he's got it, now I've got it, now you've got it, now I've got it. But you could have the situation here where we have some, big kid playing with a little brother, and mama's come in the room and said, you need to share with little brother, but the big kid will share, but my turn's going to be longer than your turn, where the big atom is going to hog the electrons, be a ball hog, right? He's going to keep the toy longer than he's going to let the little brother play with it. He'll let the little brother play with the toy for a while because, mama just came in and told him to. But we're going to kind of give it and then take it right back and hold it more, and then give it, then take it right back. This would be called polarity. Now this looks like a fairly fair game here. We have, looks like that's being pulled this way and that's being pulled this way, and if we're having a tug of war, everything's equal. And this is called nonpolar covalent bonding. A giveaway that it's nonpolar is that I can see a nice straight molecule. That's a hint if you have a picture of a molecule. So this is carbon dioxide. It's got a carbon in the center and then 2 oxygen molecules like that. And it is your classic nonpolar molecule. Electrons do circle the carbon, then they'll jump to the oxygen, back to the carbon, and back to the oxygen, and so on and so on and so on. This is equal sharing. It's still covalence, they're still sharing, but it's perfectly equal sharing. Each kid has the ball the same amount of time as the other kid does. Lipophilic molecules are nonpolar. We've seen that before. This is why. Because they share the electrons equally as they pass them back and forth to each other. And because of that, they're not going to mix with water. We're going to find out that water is the classic polar substance, and fats, nonpolars, and water, polar, don't mix. Now, if you're thinking to yourself, wait a minute, I thought carbon dioxide mixes with water. And you would be right. Carbon dioxide does actually dissolve in water. The chemistry is complicated, and I honestly can't explain it to you all the way except by saying the very basic. When you mix CO2 with water at just the right levels, you do see carbon dioxide become polar momentarily. Okay, what about if the sharing is unequal? What if there is a big kid and he does hog the electrons more than the other kid? Well, typically we will see a bending of the molecule, kind of this V-shaped bend to the molecule in space. Now, you can't see that unless it's printed that way for you, but I do see this bent here. And these are three examples of looking at water side by side by side. Again, water is your classic polar molecule. Water is polar, water is polar. And the statement here underneath that is hydrophilic molecules are also polar. Another way you can say that is they're water soluble. They'll dissolve in water if they're hydrophilic. Non-equal sharing, a polar covalent bond. Here, this hydrogen bond is a different game. So let's think real quick. Let me give you a couple of root words that are really handy here. Intra, see if I can get that spelled better, molecular, and intermolecular. So inter versus intra. Those two prefixes, intra and inter, are opposites. Intra typically means within, and inter means in between. These are really good root words to know. They come up all the time in all kinds of sciences, especially anatomy and physiology. So let's think about this for a minute. If I talk about a molecule of water, and I ask how it's held together on a standardized test, that would be its intramolecular bonding. How is it held together within? Like, how is this H and O held together? Well, we know the answer to that. We just looked at it as a polar covalent bond, right? Because it's got that bend to it. And water is polar, we remember that. So if you're ever asked what holds water together, that would be polar covalence. However, you know that if you have a bucket of water, it kind of sticks to each other, right? Water kind of sticks to each other. Other molecules of water kind of form a film even sometimes, right? And this is accomplished by something called intermolecular bonds. Those bonds that are in between water molecules. A totally different question. Those bonds are not polar covalent bonds. And the first way I can tell is because I see the dashed or dotted lines. Usually a giveaway if you see a dot, 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 or a series of dashes, it's usually telling you that's an H bond or a hydrogen bond. Okay, so this is exactly what it says, a very weak attraction formed when electropositive hydrogen, and let me go ahead and just stress this with a different color, right? These hydrogens are electropositive. See that here? Electropositive. And this giant oxygen is electronegative, but so is this one. And so what's happening here, this little hydrogen is getting pulled this way. Right? This little hydrogen right here is getting pulled this way by that oxygen, and is getting pulled this way by that oxygen. That's a hydrogen bond. All right, it's kind of a tug of war. Think of a tug of war where two giant electronegative atoms, usually like nitrogen or oxygen, are pulling on a little hydrogen in between them. If you look at this concept of hydrogen bonding and you look where water touches another medium, it says here like air, like on the surface of a pond or surface of a lake or something, right? You get this film that forms on top that I kind of mentioned. It kind of water kind of makes this goop because of this polarity, because of these hydrogen bonds in combination. And in fact, the combined strength of these hydrogen bonds makes a film, a true physical film that some organisms, if you're very small anyway, can stand on or even sometimes run on. This concept is known as surface tension. Surface tension. All right, if you enjoyed the video, thanks for watching it all the way through, and check out more in the series. See you next time.